Hi everyone, in this section we'll look at calorimetry problems with phase change. Calorimetry is a measure of the heat flow in physical processes, and often what this looks like is a calorimeter, a device that is used to create an isolated system, would be used, and then substances would be added to the calorimeter, allowed to come to thermal equilibrium, and that final temperature would be measured, and then that can be used to either identify an unknown substance or determine properties of the substances in the mixture. But okay, two things can happen when heat is added to a substance. One is that there can be an increase in temperature like we looked at in the last section. And secondly, there can be a phase change. So in this section, we will consider phase changes. And let's start with considering some ice that's taken from the freezer at negative 20 degrees Celsius. I have a graph here of temperature versus heat added. So let's imagine adding heat to that ice. We know that initially if we add heat to ice at negative 20, it will warm up that ice. So it's going to warm up until it reaches its melting point. Its melting point, of course, is 0 degrees. Now, phase changes occur at constant temperature. So at 0 degrees, any heat that's added is going to go into melting that ice. So in this phase here, we're melting the ice at 0 degrees until all of the ice is melted. Only then will heat added continue to raise the temperature. So now we have liquid water, and we're going to continue adding heat. So we add heat, and then until the ice, now melted water, or now melted ice, which is water, gets to its boiling point of 100 degrees. At 100 degrees, again, we have a phase change, which occurs at constant temperature. So we see this flat curve here as energy is added and the temperature doesn't change. Notice that this is wider than the line where the ice was melting because it takes more energy to vaporize that water than it did to melt the ice. Okay, and then after it gets to a point where now all of that water has become steam, then any energy that's added will go into raising the temperature of the steam until it gets to its final temperature, whatever that may be. I have 120 degrees at the top here. So we see that the flat lines here, the width indicates how much energy is needed for that phase change, whereas the sloped lines have a slope that's inversely proportional to c. This is because we have delta t here versus q. So if I'm going to write out this formula, we have q equals mc delta t, and we're plotting t is y and q is x. So we have delta t equals, let's do this, 1 over mc times q. So if a substance has a higher specific heat, that actually means, of course, more energy is added in order to change the temperature of that substance, which will mean a line with a lower slope so that it takes up more energy, more room on this x-axis. I think it helps to picture a graph like this when you go through calorimetry problems because each line segment here would require its own Q value. So let's look at how to find this for a phase change. The latent heat is the energy required or released in a phase change. And we can calculate that using Q, the latent heat, equals plus or minus mL. M is the mass of the substance in kilograms, and then L can be one of two constants, and we have to choose the right one. So either LF, which is the latent heat of fusion. The latent heat of fusion is the energy required to convert 1 kilogram of that particular substance to a new phase. And this would be used anytime the phase transition involves a solid. So either a solid that is melting into a liquid or a liquid that's condensing into a solid, we would choose the LF value. And these can be found in a table, so it's specific to that substance. Okay, or we can choose LV, which is again the amount of energy required to convert 1 kilogram of that substance into a new phase. But in this case, it can be we'd use this if we're doing a transition that involves a gas. So either a liquid that's vaporizing into a gas or a gas that's condensing into a liquid. And this could be the amount of energy required or released in that phase change. So we do have to add a sign here for any phase change terms. We didn't do this for Q equals mc delta T for the temperature change terms because it naturally came out of the temperature change, but we do need to add the sign if it's a phase change. So decide if the phase transition requires energy, then it would be positive. So this is going from solid to liquid to gas. Those transitions require energy. If the phase transition releases energy, we'll make the term negative. So that's the other way. Gas to liquid to solid would release energy. When we have a calorimetry problem, we still need to have conservation of energy apply. So the sum of all the Q values for the system equals 0. However, now we need to have a Q value for every phase change that occurs as well. So, and then make sure to add the right constant and the right sign in for those phase change terms. Okay, let's look at some examples. Example 2, water has the following latent heat values. LF equals 333 kilojoules per kilogram and LV equals 2,260 kilojoules per kilogram. How much energy is required to melt 200 grams of ice? What about to vaporize 200 grams of water? Assume they are already at the melting or boiling point. All right, to melt ice, Q melt, this does require energy since it's going from a less energetic to more energetic state. So it will be positive MLF, that's the latent heat of fusion, since it's transitioning from a solid to a liquid. So we have 0.2 kilograms times 333 kilojoules per kilogram. It's okay to leave it in kilojoules. We'll just end up with an answer in kilojoules, which is 66.6 kilojoules. All right, now the energy required to vaporize that water into vapor or steam is also positive. It requires energy, MLV, so 0.2 kilograms times 2,260 kilojoules per kilogram gives me 452 kilojoules for the vaporization. Example 3, suppose you want to raise the temperature of 100 grams of ice from negative 20 degrees Celsius to generate steam at 120 degrees Celsius. How much energy is required? We're going to need a few constants to do this, so you can find them in the data table first. We'll need the latent heat of fusion of water, the latent heat of vaporization, and then the specific heat for ice, water, and steam. The specific heat depends on the phase, so we'll need one for each phase. Okay, and now let's go through what happens to the ice in steps and calculate the heat required in each step. So first we take that ice from the freezer and it's going to warm up. So the first step is that we'll warm the ice to 0 degrees Celsius. So we'll have the mass of ice, C ice, delta T for ice in this step. All of the masses will be the same, in fact, because it's the same substance, so we can just leave that as M. So this is going to be 0.1 kilograms times 2100 joules per kilogram degrees Celsius, and then times 20 degrees, since the change in temperature and this step is 20 degrees, it's 0 minus negative 20. And this gives 4,200 joules. Okay, now at 0 degrees, the ice is at its melting point, so the next thing that happens is that the ice melts. And Q for melting the ice will be MLF. We use the latent heat of fusion since it's going from solid to liquid. And again, it's positive because it requires energy in this step. Okay, so this is 0.1 kilograms times 333,000 joules per kilogram, which is 33,300 joules. Now that ice is melted and it's in the water stage. So the third step is that now that water, or now that melted ice will warm the melted ice, to 100 degrees Celsius so that it will be at its boiling point. And water, seawater, delta T for water, so 0.1 kilograms, 4,186 joules per kilogram degree Celsius. So now that the melted ice is in the water stage, we use C for water. And then this is a temperature increase of 100 degrees Celsius. And this one gives me 41,860 joules. All right, moving on, now that melted ice, which is water, is at the boiling point, so we're going to vaporize the water, or that's what will happen next as long as energy is continuously added. So let's see how much energy needs to be added. Oh, I'll just add in a label here. It will be the mass of that water ice steam times the latent heat of vaporization, since it's going from a liquid to steam in that case. So this is 0.1 kilograms times 2,260,000 joules per kilogram. So 226,000 joules is what we get for that step. And then the last step, number 5, is that now we're going to warm the steam to the final temperature of 120 degrees Celsius. So this is step 5. We'll have that mass times C for steam, delta T for steam. So 0.1 kilograms times 2010 joules per kilogram degrees Celsius. And then another temperature increase of 20 degrees, so 120 minus 100. And this is 4,020 joules. All right, so now in the last step, we want to find the total Q value, which will be the sum of all the individual Q values that we found previously. So we'll add up all of the energy to find the total energy required. So we have 4,200 joules plus 33,300 joules plus 41,860 plus 226,000 plus 4,020 joules. And that's all 5 terms we're adding up to give a total energy required of 309,380 joules, which is the energy required to melt that ice from the freezer at negative 20 degrees and then eventually convert it into steam at 120 degrees. Example 4, a 0.5 kilogram block of iron is removed from an 800 degree furnace and immediately dropped into 0.2 kilograms of water at 20 degrees. What fraction of the water boils away? Neglect any heat transfer to the container. Okay, so I've made a list again of all of the data that we have, and again we need to find the specific heat of each material. So we have C for iron is 449 joules per kilogram degree Celsius, and C for water. And then we have water changing into steam, so we need the latent heat of vaporization, 22.6 times 10 to the 5 joules per kilogram. All right, then we also this time have the change in temperature per degree for each substance. So 100 degrees Celsius minus 800 for iron gives negative 700. And then for water, it's going to 100 degrees from 20, so we have an increase in temperature of 80 degrees. Since only a fraction of the water vaporizes, we know that the entire system must be at a final temperature of 100 degrees. This is because the temperature won't increase until all of it vaporizes, and it has to be at the boiling point for this boiling to happen. Also, I don't think I mentioned that the units for the latent heat, both of fusion and vaporization, are joules per kilogram, so that's why it's an amount of energy required to convert 1 kilogram of the substance. All right, so let's write out 3 terms for our calorimetry equation. So iron, to start, it undergoes only a temperature change. So we'll just have 1 Q for iron. This will be to cool that hot iron from the furnace. Okay, then water, on the other hand, will have 2 terms because we need Q to warm the water up to its boiling point, and then Q to vaporize the water. Okay, then we can fill this in. So for iron, this is just a temperature change term. We'll have mass of iron, C iron, delta T for iron. I won't expand that since we do know the temperature change. Now to warm the water, we'll have the mass of water, C water, delta T for water. And now to vaporize the water, we need to decide what sign to use and what constant to use. Of course, we need the vaporization constant, but also this does require energy, so I want to use plus M, and I've called this MS for the mass of the steam. That's our unknown, how much of it vaporizes and eventually will convert into a fraction, and then the latent heat of vaporization equals 0. Okay, so with that, we can just solve for our unknown. Let's start by solving for MS. So we'll have the mass of steam equals negative the mass of iron, C delta T, minus M water, C water, delta T water, over the latent heat of vaporization. So we can just plug in the numbers at this point. I have negative 0.5 kilograms times 449 joules per kilogram degrees Celsius times negative 700 degrees minus 0.2 kilograms, 4,186, and 80 degrees. And that's over 22.6 times 10 to the 5. All the constants are in 10 to the 5 in the table. That's why it's in improper scientific notation. Okay, and then calculating this gives 0.0399 kilograms. So that's the mass of the water that converts into steam. So it actually asks for which fraction. So let's convert this into a fraction. We'll take 0.0399 kilograms over the total amount of water, which was 0.2 kilograms. Okay, times 100. Let's do that too to get a percent. So it's 19.95%, or 0.1995 if you want to give the actual fraction. So that's about 20% of the water that boils. Example 5, your 500 milliliter glass of water is at 20 degrees Celsius, so you add 100 grams of ice from the negative 20 degree freezer. Does all of the ice melt? If not, what fraction of the ice melts? And find the final temperature of the mixture. Okay, so I've listed again our knowns. We have C for each material, and then the water is initially at 20 degrees, and the mass is 0.5 kilograms, just using this trick that 1 liter equals 1 kilogram for water, and it was 500 milliliters. And then we have the mass of ice is 0.1 kilograms. And we will need the latent heat of fusion of ice since we have the ice melting. And that's 3.33 times 10 to the 5 joules per kilogram. You can find these values really in any table of latent heats or the specific heats. There are 2 tables at the end of the Module 7 lecture problems that you can use. Okay. So here we want to figure out if the ice melts. It's not always clear. So let's first calculate the energy required to melt all of the ice. So in order to do that, let's call it Q required. We would need to first warm the ice to its melting point. So that ice is starting at negative 20 degrees, and it would need to warm to 0 degrees. I like to use long subscripts in this module. Okay, and then plus Q to melt the ice. So this is going to be M ice, C ice, delta T ice, plus, since it will require energy, the mass of ice times the latent heat of fusion. Okay, so we have 0.1 kilograms and then 2100 joules per kilogram degree Celsius. Delta T, 20 degrees, plus 0.1 kilograms times 3.33 times 10 to the 5 joules per kilogram, which gives me 37,500 joules. Okay, so now let's see if there's enough energy available from cooling the water. So this will be Q cool water, or Q available if you want. There's only one term because we're just going to cool the water, no phase changes. So that will be M water, C water, delta T water. 0.5 kilograms times 4,186 joules per kilogram degree Celsius. And then let's say we're going to cool all the water to that, to the melting point of the ice since it's melting. So we have 20 degrees and we get 41,860 joules. Okay, so at this point we can see what happens. This means that yes, there is enough energy to melt all the ice. So yes, the ice melts. Okay, so we know because there is all of this energy that can be released and the system needs to come to thermal equilibrium, that energy will go to the ice and it will melt all of the ice. We can see that this is more energy than is required to melt the ice, so that means that there is still energy left over that will then warm up the ice past 0 degrees. So we don't know the final temperature, and that's what we can find at this point. If it was the opposite case and we did find that there was not enough energy available, then we'd know that only part of the ice melted. And in that case, the final temperature would be 0 degrees because it would still be at the melting point. But there is enough energy to melt all of the ice, so it does melt. So and then now we want to find the final temperature of the solution. Okay, I needed a bit more room, so I'll continue here. So first we want to warm the ice to 0 degrees, plus Q to melt the ice. And now we know that there is some extra energy. It's not going to end up at 0, so we'll have to then warm the melted ice to the final temperature. You don't necessarily need a subscript that long, but whatever works for you. And then we're going to cool the water. Okay, so those are all of the terms that we need. And we have already found this term. So we know that to warm the ice to 0 degrees and melt the ice, that was 37,500 joules. And I called it Q required. So that we've already found. Now we haven't found this value yet because we assumed that it only went to 0 degrees and found the energy it could release, but actually we know that the final temperature will be above 0 degrees, so we don't know that term. Okay, so we have Q required plus the mass of ice. I'm warming the melted ice now. C water. So make sure you use the right specific heat value. This is why I'm not going to combine this term and this term, because it was ice and now at this point it's water, so we need to use specific heat for water. And so this is going to be to the final temperature minus the initial temperature for that ice water, which is 0 degrees, plus the mass of the water, and this is also seawater, final temperature minus the initial temperature of the water, which is 20 degrees, just so you can see the different temperatures there. Equals 0. Okay, and we want to solve for this final temperature. So I'm going to have T final equals negative Q required, and then it will be plus M ice C water, T initial of the ice, plus M water C water, T initial for the water. And then I will divide by the terms in front of TF, so Mi C water plus M water C water. And at this point, again, we can just plug in the numbers. So let's notice that T initial for ice is 0, so that whole term will be 0. So we'll have negative 37,500 joules plus the mass of water was 0.5 kilograms. Seawater, 4,186 joules per kilogram degrees Celsius times 20 degrees. And that's over our mass of ice, 0.1 kilograms, times 4,186 joules per kilogram degrees Celsius, plus 0.5 times the same constant. We could have combined that. Okay, and that gives me 1.74 degrees Celsius, which makes sense. So there was a little bit of energy left over, which went into warming the ice up to this final temperature, if you want to think about it like that. Example 6, a 70-gram bullet traveling at 250 meters per second penetrates a block of ice at 0 degrees Celsius and comes to rest within the ice. If the temperature of the bullet doesn't change significantly, how much ice melts? This is an interesting question because here what's happening is that this bullet is moving at a velocity, then it will penetrate the ice and cause some of the ice to melt. So it has an initial speed of 250 meters per second, and then it comes to rest within the ice. So if we write out the conservation of energy statement here, we have delta Ke, a change in kinetic energy, plus Q, the heat transfer, equal to 0. So this is an example where kinetic energy is actually converted into thermal energy, which melts some of the ice. So we'll have kinetic energy final minus kinetic energy initial, and plus Q equals 0. And then we can cancel the final kinetic energy. So we'll have negative 1/2 m. Let's label this mb for the bullet, v0 squared, plus m of the ice, the latent heat of fusion of the ice. So this is positive because it takes in energy to melt that ice, and that adds to 0. And now we're solving for how much ice melts, so this mass of ice is our unknown. The mass of ice equals 1/2 the mass of the bullet, v0 squared, divided by the latent heat of fusion of water. So this is 1/2, 0.070 kilograms for the bullet, times 250 meters per second squared, all over 333,000 joules per kilogram degrees Celsius. And we get 0.00656 kilograms, or 6.56 grams. So this is an example that shows that it takes a lot of energy to melt ice, right? We had a bullet that was moving at a very high speed, and its kinetic energy only melted 6.56 grams of the ice.